Question 6 involves some identified population. We don't know what it is, people, bugs, bacteria, whatever it is. But it varies over a certain number of months. So our independent variable is months. And this models the growth or decay, decrease in that population. And we are asked in Part A to determine the first derivative evaluated at 2 months and the second derivative evaluated at 2 months, and interpret the results. Well, the first derivative is of this population P of x is negative x squared plus 3x minus 1. So bring the 3 around front, that cancels with 3 in the denominator. Subtract 1 from 3, you get 2. 2 around front, that cancels with the 2 in the denominator, and so we have 3x as this term, and the coefficient of this term is just negative 1, so our derivative is, as I said, negative x squared plus 3x minus 1. Now the second derivative, we don't have the second derivative yet. So we evaluate that first derivative at 2, so wherever we've got an x, we put parentheses, and inside those parentheses, we substitute the value 2. So 2 squared is 4. This is negative 4 then. 3 times 2 is 6. And negative 4 and 6 is positive 2. Minus 1 is 1. So we have positive 1. And so at 2 months, the rate at which the population is increasing is 1. Now we calculate the second derivative, so that means that we take the derivative of this function, and we'll bring the 2 around front, subtract 1 from 2, and so that gives us negative 2x, and the coefficient of this linear term is just 3, so that gives us 3 here. So our second derivative is negative 2x plus 3. Then we evaluate the second derivative at 2, and so wherever we've got an x, we put a set of parentheses. Inside the parentheses, we substitute the value that we're evaluating at. And so negative 2 times 2 is 4, negative 4. And we add 3, and we get negative 1. So at 2 months, this population is increasing, but the rate of that increase is slowing down. It's slowing down because this second derivative is negative. So remember, the second derivative gives us the rate at which the rate of change is changing. So there's your result there. Now for 1 month, we evaluate, we have the same derivative and the same second derivative, and we evaluate them at 1. So once again, x, parentheses, x, parentheses, and you substitute in the 1. So 1 squared is 1, so this is negative 1. 3 times 1 is 2, and or it's 3, plus the negative 1 is 2. 2 minus 1 is 1. So at 2 months, that's supposed to say 1 month. So at 1 month, the rate of increase in the population is 1. Just as it was at 2 months. But then, in the second derivative, we substitute in the 1. So again, x, parentheses, substitute in the 1. Negative 2 times 1 is negative 2, plus 3 is 1, positive 1 this time. And so, at 1 month, the population is increasing, and the rate of that increase is speeding up because this is positive. So in the first instance, the rate of the increase is slowing down because this is negative, and in the second circumstance, the rate of that increase is speeding up since this is positive. Question 7 asks us to use the derivative, the first derivative of the function, to determine the following. Now, there are certain things that we can determine from the second derivative, but this asks us specifically to use the first derivative. So we have a first derivative with a really big negative y-intercept, and that that will not affect our answers in part A, but it will in part B and parts B and maybe C. So to determine the intervals of increase and decrease, we take the first derivative. 3 times the front cancels here, and 3 minus 1 is 2. And so we have x squared for the first term, 2 multiplied around the front cancels with the 2 in the denominator here, 2 minus 1 is 1, so the middle term is negative 5x, and then the coefficient of the linear term is 6, so this is our first derivative. We set that first derivative equal to 0 and solve to find these two critical values. And then on a number line, we mark those here, 2, 3, here's negative 1, 0, 1. So we mark 2 and 3 here on the number line. Then we evaluate the derivative, not the function, the derivative. We evaluate the derivative at some point in this interval. And I've chosen 0 because there's nothing really easier than 0. And so 0 squared is 0, negative 5 times 0 is 0, and what we're left with is 6. So this derivative is positive at 0. It is then going to be positive on the entire interval, which is what we see here. And so on that interval, we know that the function is increasing. Then we choose a point here in this interval, and the best one that I could come up with was 5/2, which is also 2.5, but I prefer working with the fractions. To me, I can do those in my head as opposed to the 2.5, which truthfully I suppose I could multiply that in my head. But it's much easier to work with fractions for me. If you want to put 2.5 in your calculator, go right ahead. It doesn't matter to me as long as you come up with the right value. So we're going to evaluate the derivative again at 5/2. And so wherever we've got an x, we put some parentheses. Wherever we've got an x, we put some parentheses. And we substitute that value in. So 5/2 squared is the numerator squared, 25, over the denominator squared, 4, minus, and then for this term, that's 5 times 5 is 25, and that's just multiplied by the numerator, and so the denominator is 2, and our constant term is just 6. And 25 over 2 would be 50/2, and 50/2, 50/4, 25 over 2 would be 50/4, and 25 over 4 minus 50/4 would give us a negative 25/4, and 6 over, or 6 is 24 over 4, so that's a negative 25/4 and a positive 24/4. You put those together, you get a negative 1/4. And so at 2.5, the value of the derivative is negative 1/4, and that means that on this entire interval, the function, or rather the derivative is negative, and so the function is decreasing on that interval. Finally, I chose 4 to evaluate in this interval. Could have used 5 as well, but 4 works fine. And so where we have parentheses, where we have an x, we put parentheses. Where we have an x, we put parentheses. Inside those parentheses, we put the 4. And so 4 squared is 16. 5 times 4 is 20, so 16 minus 20 is negative 4. Plus 6 is 2, which is positive. So on this entire interval, the first derivative is positive, which means that the function is increasing on that interval, and that is summarized here. So the function is increasing on the intervals negative infinity to 2, not including 2 because it's 0 at 2, union, okay, this interval, and this interval 3 to infinity, again, not including 3 because it's neither increasing nor decreasing there because the derivative is 0. Then in the middle, from 2 to 3, the function is decreasing. Okay, and that answers everything we're asked for in part A. B, we're asked to locate any local extrema, a local minimum and or a local maximum, which is what this function has, one local minimum, one local maximum. And so we see that since the derivative changes from positive to negative at 2, we know that the function is increasing before 2 and decreasing after 2, so that means we have a local maximum there at 2. So we evaluate the function, not the derivative, we evaluate the function at 2. So we put a 2 here, 2 cubed is 8, put a 2 here, 2 squared is 4, 5 times 4 is 20, and 6 times 2 is 12. And when you combine all three of those, 8 thirds, 20 halves, which is 10, divided by, added to 12, you combine all those, the common denominator, and then reduce, you arrive at 14 thirds. So 14 thirds minus 237 is negative 697 over 3, negative 697 thirds, which as a decimal is negative 232.33, negative 233 and a third, and the 33 with a line over it just means that these 3's continue to repeat and never terminate. And then we see that the derivative changes from negative to positive at 3, so the function's decreasing before 3 and increasing afterwards, and so that means that the function sort of bottoms out there, and so we have a local minimum there. So then we evaluate the function at 3. 3 cubed over 3, 3 cubed is 27, 3 squared is 9, times 5 is 45, 6 times 3 is 8, and when you combine all of these with a common denominator and then reduce, you will come up with 9 halves, 9 over 2. You subtract 9 halves, or subtract 237 from 9 halves, you get negative 465 over 2. And so that value is then negative 232.5. That is the value of your local minimum, the function value of the local minimum. In part C, we need we're asked to determine the absolute maximum and absolute minimum of this function on this interval 2 to 4. Well, to determine the absolute maximum and minimum on an interval, you evaluate the function, not a derivative or anything else. You evaluate the function at the endpoints and any critical values in between. Well, the only critical value in between 2 and 4 is 3, and so we have evaluated the function at 3, and we found that to be negative 232.5. The other, and one of the endpoints, the left endpoint of the interval is 2. We've already evaluated the function at 2 and found that to be negative 232.33, repeating. And so now all we have to do is evaluate the function at 4, which is the other endpoint, the right endpoint of the interval. And so we put 4 here, 4 cubed over 3, 4 squared times 5 over 2, plus 6 times 4. And you combine all those with a common denominator and reduce, and you'll have 16 thirds. You subtract 237 from that, and that gives you negative 695 over 3, which is negative 231.66. Again, the line means repeating and never terminating. So, negative 232.5 is just a little to the left of negative 232.33, which is just a little to the left of, a little more to the left of negative 231.66, So this value is our absolute maximum on that interval, and this value is our absolute minimum on that interval.